You know, when you look out the window of a commercial jet at like 35,000 feet, you see that massive silver wing cutting through the clouds.
Oh, yeah. And it looks absolute, completely solid.
Right, like this single unyielding object. You expect it to be basically a brick wall.
Which makes sense because psychologically, we inherently trust things that seem solid and immovable,
Yeah.
especially when, we're relying on them to keep us in the sky.
Exactly. But then you hit a patch of turbulence, and that entire wing bends upward.
It visibly flexes.
Yes. And for a split second, your brain just panics because solid things aren't supposed to bend like that without breaking.
I mean, it goes against all our instincts. But if that wing didn't bend, if it were truly as rigid as your brain wants it to be, it would just snap right off the fuselage.
Which is a terrifying thought.
It really is. What you are actually seeing when that wing flexes is the culmination of, well, 12,000 years of human obsession.
Obsession with manipulating the molecular structure of the Earth.
Precisely.
So today, we are taking a deep dive into the hidden world of aircraft metallurgy. We've got our hands on an incredibly detailed FAA textbook, Chapters 6 and 7, on aircraft materials and corrosion, to be exact.
It's a fantastic source. It really serves as a bridge between ancient history and modern aviation.
It totally does. And our mission today is to trace that journey. We're going to explore how human progress has literally hinged on our ability to manipulate metal.
From the first primitive copper tools all the way to the highly specialized alloys keeping modern aircraft safely in the sky today.
So to really grasp the engineering inside, say, an Airbus or a Boeing, we actually have to rewind a bit.
A big bit. About 12,000 years.
Right. Back to when humanity first realized that rocks didn't just have to be rocks.
Yeah, someone somewhere made this incredible discovery. They found out that if you took a specific type of ore and applied extreme heat, about 1,000 degrees, it extracted something entirely new.
It formed this coppery color.
Yeah.
Which, I mean, that's an incredible leap in human logic on its own.
Oh, absolutely. But the real breakthrough wasn't just extracting the copper. It was what they did to it once they finally had it in their hands.
They hit it.
They hit it repeatedly with a hammer.
It's just brute force.
Exactly. And the technical term the text uses here is work hardening.
Work hardening.
Yeah. By smashing this copper over and over, they weren't just changing its shape, they were physically compressing its crystalline structure.
Oh, wow. So they were literally packing the atoms tighter together.
Right. And that made the metal significantly harder and more durable. It turned this soft chunk of copper into a functioning axe or a cutting tool.
So this is really humanity's first real foray into changing the physical properties of a material, just through pure brute force.
It was. But as populations grew, brute force just wasn't enough anymore. Mechanical force has its limits when you're trying to meet the demand for better tools.
So that brings us to the next massive pivot, right?
Yeah.
The alloying process.
Yes. Eventually, early metallurgists figured out that if they added tin to the copper while it was in a liquid smelted state, they created something completely new.
Bronze.
Bronze. We moved from merely hitting a single element with a hammer to intentionally mixing elements together.
Creating a material that's actually greater than the sum of its parts.
Exactly. And as civilizations expanded, that demand drove the discovery of the metal that would eventually spark the Industrial Revolution.
Steel.
Yes. But to make steel, you have to alloy iron with carbon.
Because iron on its own is, well, surprisingly impractical, right? The source notes that pure iron actually lacks the necessary strength for heavy construction.
Right. It's too soft. It needs a chemical partner.
But early on, making steel was incredibly expensive and really slow. They could only produce it in these tiny batches.
Until industrialists figured out a massive breakthrough.
Right. The text outlines this method where they forced a huge amount of hot air through the melted iron and carbon. And okay, let's unpack this. Because when I read this, I immediately thought of baking bread.
Baking. Okay, walk me through that.
Well, think about it. Iron is your flour. It's the base. But you can't build a strong structure with it alone.
Okay, I'm with you.
And carbon is your yeast. You only need a little bit, but it fundamentally changes the dough.
Right.
But the magic doesn't happen until you put it in the oven. That massive blast of hot air forced through the melted iron and carbon, the oven heat activating the yeast. It fundamentally changes the chemical structure to give us modern steel.
Okay, I see where you're going with the yeast. A tiny amount of carbon entirely changes the iron. But the hot air part?
Yeah.
That's not activating anything. I mean, forcing air into liquid metal. Wouldn't your instinct be that adding oxygen causes rust?
Oh, Yeah, I guess oxygen and iron usually means oxidation, like it degrades the metal.
You would think so. But in a liquid state, at those extreme temperatures, the oxygen in that blast of air actually grabs onto the excess carbon.
Wait, it grabs it.
Yeah, and all the other impurities in the iron, it binds to them and literally burns them off as a gas.
Oh.
So it's not a mixing process at all. It's a massive, violent purification system. The air blast strips away the weaknesses, leaving this perfectly bonded iron-carbon matrix.
If we connect this to the bigger picture, humanity shifted from physical manipulation like hitting copper
Yeah.
to this incredibly complex chemical mastery.
Oh, wait, I usually say that, but yes, exactly. We achieved chemical mastery, and because of that specific purification process, today, more tons of steel are made every single year than all other metals combined.
Wow, okay, so we have this perfect steel, we have chemical mastery, we just start stamping out airplane parts and take to the skies.
Not even close. No, because the sky is an incredibly hostile environment. An aircraft isn't just sitting there, it's being blasted by freezing temperatures.
Roasted by engine heat.
Pressurized, depressurized, and rattled by turbulence. To survive all that, engineers can't just slap a slab of steel on a wing.
So they have to engineer specific physical properties for every single inch of the aircraft.
Exactly. Which introduces the whole push and pull of metallurgy.
And the FAA textbook meticulously breaks down how these materials behave under stress. Let's look at strength versus hardness versus toughness.
Those are key.
So strength is basically the ability to resist stress without breaking. Hardness is resistance to denting or scratching, which, by the way, we still increase using that ancient trick of cold working hitting it, as well as heat treatments.
Right.
But toughness, toughness feels like it should be the exact same thing as hardness.
It's a super common misconception, but they are very different. The text uses the examples of hammer faces, metal punches, and wrenches.
Okay.
These tools must be incredibly tough. Because if a metal is only hard but lacks toughness, it's actually dangerous.
Really? Why?
Because toughness is the ability to absorb a massive impact, to deform just a little bit without actually fracturing.
Oh, which perfectly explains the ultimate enemy of toughness.
Yeah.
Brittleness.
Yes. A brittle metal will break or crack before it bends or changes shape at all.
And the source lists cast iron, cast aluminum, and very hard steel as brittle.
Think about dropping a cast iron skillet onto a concrete floor.
Oh, it doesn't dent.
Exactly. It cracks. It might even shatter into pieces. That is brittleness. And when you are designing a vehicle carrying hundreds of people through the air at 600 miles per hour.
Brittle structural components are your absolute worst nightmare. You need materials that give, not materials that snap.
Precisely.
Okay, so we avoid brittle metals. But then we have to deal with the engines. Jet engines generate an insane amount of heat, which introduces our next enemy, thermal expansion.
Right. It's a fundamental law of physics. Everything expands when it gets hot and shrinks when it gets cold.
Because when you add heat, you are basically adding energy.
Right, yeah. The atoms literally start vibrating and pushing each other apart.
But the textbook points out something really interesting. It says, a metal's coefficient of thermal expansion is generally inversely related to its melting point.
And this is where the atomic bonds really come into play. Take titanium, for example.
Okay.
It melts at a blistering 1,660 degrees Celsius.
That is incredibly hot.
It is. And because its melting point is so high, it means its atoms are gripping each other with incredible force.
Oh, I see.
So when it gets hot, those atoms actively resist the urge to vibrate apart. It has a very low thermal expansion. It holds its shape.
Meanwhile, the text says lead melts at a super low 327 degrees Celsius.
Right. Its atomic bonds are relatively weak, so it expands significantly the moment it gets warm.
So the higher the melting point, the tighter those atoms are holding onto each other.
Exactly.
Which brings us to the property that completely blew my mind. Going back to thinking about that airplane wing bending out the window. Elasticity.
Oh, elasticity is everything.
The source introduces something called Hooke's law, which defines exactly how metal distorts under load. And it outlines a curve with 5 distinct stages.
Hooke's law really dictates the core of all structural engineering. It's the map of how a material behaves right before it fails.
Okay, let me try to break these 5 stages down, and you tell me if this tracks. Let's use a thick rubber band as our piece of metal.
A rubber band?
Sound good. So stage 1 is the elastic limit, or yield point. This is the boundary of Hooke's law. You pull the rubber band a little bit, you let go, and it snaps perfectly back to its original shape.
Right. No permanent damage is done. The aircraft wing hits turbulence, it bends upward into stage 1, the turbulence stops, the wing drops right back to perfectly level.
Okay, but if you pull that rubber band too hard, you push past Hooke's law and enter stage 2, the strain hardening region.
Yes.
You pulled it so far that it's permanently distorted. It will never snap back to its original size. But here's the weird part. The text says the act of stretching it has actually made the metal harder to keep pulling.
This is that cold working effect happening at the microscopic level again.
Wait, from just pulling it?
Yeah. To understand why it gets harder, imagine a perfectly stacked pyramid of oranges at a grocery store. If you gently push the top of the pyramid, the layers of oranges easily slide over each other. That's soft metal. But when you stretch a metal past its elastic limit when you enter stage 2, you are violently crushing those oranges together.
Oh.
The perfectly ordered rows become jagged, tangled, and completely misaligned. They can no longer slide smoothly. By damaging that perfect crystalline structure, you've actually made the metal much more rigid.
That makes so much sense. The damage literally creates a traffic jam of atoms.
Exactly.
But eventually, if you pull even harder, you hit stage 3, ultimate strength. This is the absolute maximum stress the material can take. It is screaming at you.
It has absorbed all the energy it possibly can.
Which quickly leads to stage 4, the necking region.
Mhm.
This is where you see one specific spot on the rubber band suddenly get really thin and pale.
It's yielding entirely.
And finally, stage 5, rupture or failure point, snap.
It's a perfect visualization of the textbook's curve. And this goes right back to your instinct at the beginning of the deep dive when you said you expect an airplane wing to be completely rigid.
Yeah, my brain still tells me that rigid equals safe.
And that is exactly what we have to unlearn. When you are a passenger flying through a storm, you desperately want the plane to rely on elasticity.
Because if it didn't,
If engineers built a wing out of a metal that was incredibly hard but had no elasticity, say, something like glass wouldn't bounce in the wind. The moment the aerodynamic stress exceeded its ultimate strength, it wouldn't bend to absorb the blow.
it would instantly bypass stages 1 through 4 and hit stage 5, rupture.
Right. By using metals with a wide elastic limit, the aircraft can absorb the violent, unpredictable energy of the sky by flexing rather than shattering.
So wait, if an airplane wing bends, it's not failing.
Not at all. It's not struggling against the atmosphere. It's breathing with it. It's performing exactly as engineered.
That is wild. So how does the aviation industry actually deploy all this science on the tarmac?
Well, the text divides aircraft metals into 2 broad categories. Ferrous, which contains iron, and non-ferrous, which doesn't.
And we know pure iron alone is basically useless, so we rely on steel alloys.
Exactly. And the FAA uses a highly specific numbering system to identify them. This numbering system isn't just trivia, by the way. It is life or death practical information for an aviation mechanic.
The code is actually pretty clever once you know how to read it. The second digit gives the approximate percentage of the major alloying element. But the last 2 digits are the most critical. They indicate the exact percentage of carbon.
Right.
So low-carbon steel has between 0.10% and 0.30% carbon. Because the carbon is so low, it's easily shaped and welded. It's mostly used for secondary structural parts.
But if a mechanic is replacing a critical bolt on the landing gear, they can't just grab any piece of metal off the shelf.
Not at all. They rely on that specific code. The text highlights SAE 2330 steel as a superstar here.
Right, SAE 2330. That 30 at the end tells the mechanic exactly how much carbon is inside 0.30%.
And if they accidentally put a 10 bolt where a 30 bolt belongs.
That landing gear could snap upon touchdown. The carbon dictates the metal's entire destiny.
Wow. And what makes SAE 2330 so special is what they add to it, right? They add nickel.
Yes, nickel increases the hardness, the tensile strength, and that crucial elastic limit we just talked about.
All without decreasing its ductility, its ability to bend without breaking.
It perfectly balances strength with forgiveness. That's why it is used extensively for the parts holding the entire puzzle together. The bolts, terminals, keys, and pins.
Then you have another famous ferrous alloy, 18-8 stainless steel. This is the corrosion-resistant steel. They use it for exhaust collectors, cables, and tie rods. But what does the 18-8 actually mean?
It's the recipe. It stands for 18% chromium and 8% nickel.
And the chromium is the secret weapon against rust, right?
It is. When that 18% chromium is exposed to the oxygen in the air, it reacts instantly. It forms an invisible microscopic shield of chromium oxide right over the surface of the steel.
Which prevents oxygen and water from ever touching the underlying iron.
Exactly. And the most amazing part, if a rock kicks up and scratches the steel, exposing fresh iron, the chromium in that newly exposed area instantly reacts with the air to form a new shield.
It's essentially a self-healing metal.
It really is. But as incredible as these steel alloys are, an aircraft cannot be built entirely out of them.
Because steel is dense. If you built a whole jetliner out of 18-08 stainless, it would simply be too heavy to fly efficiently.
Which is where the non-ferrous metals, the ones without iron, step onto the stage.
Aluminum is the undisputed king of the fuselage here. Its outstanding characteristic is its lightweight. Now, the source does note that some aluminum alloys lack a hardening element, meaning they melt at relatively low temperatures.
Right, but they are perfect for making up the massive bulk of the aircraft's body.
But then you have the engines, the turbine hot sections, the turbochargers.
Well, the environment inside a jet engine is a literal inferno. Aluminum would melt into a puddle in seconds.
And standard steel would warp and lose its structural integrity.
Exactly. Here, engineers rely on specialized non-ferrous superalloys like Manel and Inconel.
The source notes they look just like stainless steel, but their behavior is entirely different.
Because they are primarily made of nickel-copper and nickel-chromium blends. Remember how we talked about thermal expansion and atomic bonds?
Yeah.
The bonds in Inconel are so incredibly strong that they maintain their grip on each other even when blasted continuously with the thousands of degrees exhaust gases of a jet engine.
They simply refuse to yield to the heat.
They hold the line.
So what does this all mean? I was thinking about this massive lineup of materials, and it really feels like casting a movie.
Casting a movie?
Yeah, you don't just cast one superstar. You can't just make the whole plane out of steel, or it won't get off the runway.
True.
And you can't make it all out of aluminum, or the engines would liquefy. You need an ensemble cast.
Ah, I like that.
Yeah.
Every material plays a highly specific role.
Exactly. You need the heavy-lifting character actors, that's your Inconel and Manel,
Okay.
sitting inside the blazing heat of the engine doing the dirty work without complaining.
Right.
You need the lightweight, agile leads, that's the aluminum, making up the massive wings and body so the whole thing can actually soar.
And you need the totally dependable supporting cast.
Yes, those SAE 2330 steel bolts and pins quietly holding everyone else together under immense stress.
What's fascinating here is that it really is a massive, high-stakes balancing act of contradictions. Aviation engineers are constantly balancing extreme heat resistance against the desperate need to reduce weight.
They are balancing ultimate rigid strength against the absolute necessity of elasticity.
They even have to balance structural integrity with things like electrical conductivity.
Oh, right. The source mentions that electrical bonding is essential across the entire aircraft.
Because if the metals don't conduct electricity properly to dissipate static charge, a lightning strike or even just friction from the air could completely blind the plane's communication radios.
Every single microscopic property matters.
It is a synchronized symphony of chemistry and physics.
Which really brings us full circle. We've covered a massive expanse of human ingenuity today.
We really have.
We started 12,000 years ago with early humans finding a glowing rock, waiting for it to cool, and hitting it with a hammer to compress its atoms and make a copper axe.
And we followed that exact same foundational desire to manipulate the Earth's molecular structure all the way up to today.
Up to engineers strategically placing self-healing stainless steel cables and casting Inconel turbine blades to survive the heart of a modern jetliner.
It's a profound legacy. And the next time you step onto an airplane, I highly encourage you to look past the paint, the carpet, and the seats.
Look at the metal.
Yeah. Think about the invisible, highly engineered properties operating all around you. Think about the elasticity in the wings absorbing the violent energy of the sky.
The thermal expansion being carefully chained down inside the engines.
And the microscopic chromium shields constantly repairing themselves in the air.
It completely changes how you look at the world. And I want to leave you, our listener, with a final thought to ponder today.
Great.
The text explicitly points out that humanity has been work-hardening metal, physically crushing those atomic oranges together for 12,000 years. 12 millennia.
It's a long time.
And that primitive concept is still a foundational step in advanced aerospace engineering today. It makes you wonder, as we look toward building habitats on Mars or designing deep space starships,
What seemingly primitive human process are we doing today that will still be used?
exactly, what basic thing, maybe something we are doing right now in our kitchens or our garages, will be the foundational engineering principle holding our future together 10,000 years from now?
That is a wild thought.
When you look out that window at 35,000 feet and see that silver wing bend, you aren't just looking at a solid piece of metal. You are watching 12,000 years of human history, flexing and holding you safe.